Morning, guys. So I just realized my last lesson was getting to be a little bit long, so I've decided to just split this off here as sort of part two. I'm just going to rehash what we've been doing over the last lesson or so. We started looking at the technique of a titration. In this example here, we were doing an acid-base titration. Basically, by running through a neutralization reaction, I want to do it so quantitatively that basically when the color changes, I know when to stop. I know at that case there when there's no limiting and when there's no excess, and I would have a good count of the unknown particles in the solution. We saw towards the end of last lesson how we can actually convert that over to actually find the concentration of NaOH. Here's back to our virtual simulation here. I'm just going to finish off with part two of this part. I'm going to walk you through another set of titrations. At this point here, we have started off with our primary standard here, which is KHP. This was a solid. I had calculated how much mass I would need. We standardized it in a volumetric flask. The volumetric flask is more quantitative. It's a really nice marking versus beakers don't. Of course, in my correct way of actually making the solution, I first dissolved it in a beaker. You mash it up a little bit here. Just make sure it's less than the 100. That's the total volume volumetric. You transfer it in. You might find this residue left over in the beaker. Add in a little bit more water. Transfer those rinsings also into the volumetric. Eventually, when you're satisfied that all of this went into the volumetric, you can just add water up to the mark. Be really close when you're up to this narrow neck part here. You would probably use an eyedropper pipette here so that the volume, it increases really, really quickly. You want to make sure that the bottom of the meniscus is actually directly matched up with the line. If you accidentally overshoot at this point here, you would actually need to redilute a new sample because there's no way of grabbing that powder back out. Again, the reason why we pre-make the solution here in a beaker is because a beaker has a much wider mouth, a lot easier to take a stir stick and mash up the powder when you're in the volumetric flask. Although it's a nice quantitative, it's really well calibrated for 100.00, that narrow neck makes it really hard for you to dissolve powder inside. After you're guaranteed that it's 100, what we did is we actually poured it back into the beaker. It's okay that it actually doesn't line up with the 100 ml on the beaker marking anyways, because I already am confident that it's actually 100. One other advantage of doing that way here is when we actually pull out our pipette, we generally don't want to pipette out of volumetric flask because, again, that narrow neck here may make it a little bit more precarious. But now that it's in a beaker, we can very simply leave the pipette here underneath the beaker. You soak up, in this case here, 10 milliliters. It acts like a straw. We transferred it in. I did this 3 times, so we can actually do 3 trials. For titration, the whole point is we want to hopefully have at least 2 trials, if not all 3, hitting pretty close the same volume reading before we actually do our stoichiometry. In the past, chemists used to pipette by mouth, so instead of actually having a suction bulb here, they would actually really literally like a straw put their mouth on this end. You can imagine here, whoops, if I suck up too much, then you just drank your solution. Totally not a good safety procedure. Nowadays, we just have a pipette bulb here. It has a little bit of negative pressure. As long as the pipette is underneath the solution, as you unleash that pressure here, it's going to basically soak up the solution. You do want to calibrate it just for that one single mark. Pipettes either come to us 10 milliliters or 25 milliliters here. This one here happens to be a 10 milliliter pipette. At this point here, I'm actually ready to do my second titration. So far, we've taken our primary standard. I made a standardized solution. I know this concentration. This was the 0.900 molar solution. I knew that concentration really, really well, and I used that to actually titrate the NaOH. The NaOH at first was already told to me. It was about 1 molar NaOH. What we found through our titration was it was only 0.92. So they're close, but again, the whole point of a titration is to be more precise. I would even like to be more precise if I can. Unfortunately, my titrant volume, how much base I dropped in was somewhat less than 10, and that left me only with 2 sig figs if you account for the error. What I'm going to try to do in setting up this next part here, we're going to actually hopefully have enough NaOH. This is totally a problem that we can happen here. We spent so much NaOH here. I standardized it. Oh, I know this solution here is now perfectly 0.92 molar, but I'm realizing, oh shoot, I don't have a lot of it left. I can't, if I have a stock bottle of NaOH here, I can grab some more, but I can't then make a fresh sample of NaOH because every time you make NaOH, the concentration will be a little bit different. Even if you follow the same recipe, you're like, okay, I want to make exactly 0.92. I would need to go through exactly the same procedure again, standardize the NaOH all over again, and make sure you have enough NaOH to actually titrate the about 1.1 molar HCl. Fortunately for us here, because their acid is roughly 10 times less concentrated, if I did a straight titration between the NaOH I had left and the HCl, we're going to find 1 drop of this is going to be approximately 10 times concentrated of this. The color is going to change really, really quickly. again, what you're going to try to do is you're going to try to dilute the concentrations down, roughly speaking, so that they're going to be similar, so that it's going to be roughly, if I use 10 mils of my HCl, I want it to take roughly 10 milliliters of NaOH. And in fact, I'm going to demonstrate for you how I'm going to do this dilution. I'm going to dilute it a little bit more than I need to. Hopefully, I'll get more than that 10 milliliter titrant volume, and you actually see that we actually get one more significant figure out of it. So fortunately for me here, first thing, I still have my virtual lab open here, but I still have some NaOH. It's still fresh. It's uncontaminated here. I'm just going to pour this back into a beaker of some sort. I want to do this dilution, and what I'm going to dilute it by here is maybe I want to dilute by a factor of 10, so my 0.92 molar would drop to 0.09, and in case that this one here was also like 0.09 or so, maybe I want to dilute a little bit more than 1 in 10. At first, you might think about pulling out a grad cylinder. Grad cylinder is very convenient, right? And in the end, I'm going to need a lot of it, so I'm going to pull out, I want to pull out a 50 ml grad cylinder. Right, so 50 ml grad cylinder, we did the dilution lesson. Basically, it's a volume ratio. So if I want, let's say, 50 mils of my diluted sample, I need to dilute 5 into 50. So that's by a factor of 10. Therefore, my concentration would drop from 0.92 to 0.092. So I could do that with a grad cylinder here. Grad cylinders are much better than beakers in terms of their labeling, in terms of how quantitative their marks are, but still not the greatest. If you are really doing this for real, you will actually want to dilute also using a volumetric. That same container that we actually made the KHP solution, you'll notice the volumetric solutions also come to us many shapes, many sizes here. Let's make up 100 mils of solution again. I realize I don't have as much solution in here. The burettes are also really well calibrated for, so you can just actually dispense the burette directly in the volumetric. Ideally, I would still have some NaOH left over, and I can just use that to dilute. But in this case here, I realized, I actually emptied out my NaOH when I first put it in the burette here. I'm just going to put it into the volumetric flask, drag this in. What I want to do is let's say, 10 milliliters of my NaOH. And once I add it up to the mark, 90 milliliters, then it's going to be diluted by a factor of 10. Because I want to dilute a little bit less than a 1 to 10 ratio, maybe I'll transfer in 9 milliliters. And again, the burette is really nice in reading this one here. I can take my starting reading. In this case here, I'm just going to type in my transfer bar. Let's dispense 9 mils. So I'm roughly between 32, 33. When I drop in 9 mils, I'll probably be between 41 and 42. So let's just pour that in. That's really quantitative because I have a lot of markings on the burette, really well calibrated. I now have about 9 mils in here. And what I'm going to do, I'm going to just record that down. I transferred in 9.00 mils. And what I'm going to do is I'm going to add it up with some water. Again, you probably wouldn't take the entire flask of the water to actually dilute this completely. You'll probably pour this in either just graduated cylinder or beaker of some sort before you transfer it in. In this case here, I'm just going to be a little lazy. I'm going to drag the water directly over this flask here. So I had 9 mils ready. I can pour in maybe 90, actually no, let's just go 85 mils. I can pour in 85 safely, right? 85 plus 9 definitely will be under the mark. But as I get up close to the mark here, I definitely want to pour it in slower. So pouring in maybe 1 mil at a time. 85 plus 9 is 94, 95, 96, 97. Right, I'm getting really close, and I'm getting really close to the mark. Again, it's good to use a dropper and actually get it a little more fine-tuned. Maybe drop it in at 0.5. Right, I'm just pressing enter to drop it in there. As you're getting really, really close to the mark there, maybe drop it in at 0.05 if you can, and then basically just keep adding with the dropper until I'm sure the bottom of the meniscus is exactly at that line there. So in this case here, I've diluted 9 mils into 100 mils. You just need to keep track of how you did your dilutions. I'll show you later on the OneNote how we're going to calculate that. And now not only have I solved the problem, I was worried about running out of NaOH. I now actually have 100 mils. Of course, I want to take a fresh burette. I'm going to keep that solution just in case I need it for later. But maybe I'm going to pull out a fresh burette here. And now I'm going to still put the base in the burette. I'm going to reload this one something more than half. So let's label this one here. I'm going to pour in, let's say 40 mils, right? Maybe that'll be enough for 3 trials. I don't know. We might need to refill it later on. So keep it on the side so I know what it is. You would definitely label all these. This is now my diluted NaOH. I'm going to get rid of my acid solution and the other solutions. You can just highlight them and just delete them off. Right. This is my KHP solution. I might still need that, so I'm going to keep that on the side. Any leftover glassware I don't really need. You do want to be rinsing out your glassware, so I'm just going to pull out a fresh pipette. And now what I want to do is I want to do a titration between Now my diluted NaOH, now it's roughly in the same ballpark of the 0.1 molar HCl, and now they're closer. I should be using roughly the same amount. I'm hoping for the titration volume to be something more than 10, so that I can pick up one more sig fig. Right now, this HCl container, it's actually telling me I have some 100 milliliters. Even though this is unknown, I don't need to destroy the entire sample. In fact, what I'm going to do is I'm just going to take a small portion. The fancy name for that is called an aliquot. I'm going to pull out a couple fresh Erlenmeyer flasks, maybe just previously rinsed. I'm going to pull out 3 of them, just so that I can do it 3 times. Sorry, I'm going to pull Erlenmeyer flask here. Right. So 3 separate Erlenmeyer flasks, so I can do 3 individual trials. I'm going to decide to test 10 milliliter aliquots, so I'm going to pull out a fresh pipette as well. Pipette, so 10 ml pipette. You could even do 25 just for practice here. 25 would be actually a larger volume, and therefore you would also have more sig figs. Maybe let's do that. So let's actually pull out a 25 ml pipette just so that you can make a comparison with what's happening here. Let's take our pipette here. I'm only going to be able to do this once, because if that's 25, then I'm going to be using 25 of this, right? Just to show you with the 25 just how that looks like. So take the 25. Again, this one acts like a straw. I'm going to transfer amount here. I'm going to transfer in withdrawal 25 milliliters, suck up 25. This would be calibrated for 2 decimal places, 25.00. I'm going to transfer that into the Erlenmeyer flask here. So I'm going to pour the whole 25, and now we're really calibrated for that's going to be 25. I know roughly, because these concentrations are going to be about the same, I'm going to need to make sure I have at least 25 in here. And again, if that really is 25, I'm not going to have enough solution to actually do the next dilution. But if I'm careful for the first one, I can see what we end up with. We still need to do our phenolphthalein. I still have to use my indicator. That's going to show me when the pink color changes here. So let's go pour in maybe 3 ml of that. It's going to tell me when the color change happens. Because these concentrations are roughly similar, if I have 25 mils of my acid, I know it's going to take approximately 25. Maybe I'll toss in 20 mils safely, and I'm going to toss in maybe 0.5 at a time, and then slow it down 0.1 at a time if I can, close to as I'm getting to the 25 mark. So just to show you here, I'm going to pour the burette. This is my new diluted sample of NaOH. I can always dilute some more if we wanted to. So I'm going to just pour this in. I'm going to transfer in. Again, I could do 1 mil. I can press enter 20 times. I can go like 1, 2, 3, 4. I can do that. Or because I know it's not going to be within 20, I did 5 mils there. I can type in 15 mils. So that should be safe. Fine. I've typed in a total of 20. Now I know I'm getting pretty close. I'm thinking it's probably going to be about 25 if they're really sure it's going to be 0.1. I definitely don't want it to be dumping in maybe 1 mil at a time, maybe only 0.5 mils at a time. Maybe do that for a couple times. Maybe as I get close to the mark here, I want to even drop that down to 0.05 if I can. Again, the whole point of titration is to be really, really precise, and I just want to keep adding. This is my first trial, so I have no clue when the color is going to actually change. So I'm just going to keep pouring this in. As I'm getting close to what I believe should be the mark, I want to look for the first trace of the pink color to appear. Still hasn't appeared yet. In this case here. Oh, so there we go. So I actually hit 2 drops. Now I was adding in such tiny fractions that would be okay. In this case here, I just take another volume reading here. The final volume reading was 40.02. In this case here, I was, oh shoot, I forgot to take my starting reading here. You're out of luck. You actually need to do it again. But in this case here, I had made 100 mils of solution. We poured in 40 to begin with. Let me actually demonstrate that. Oh shoot, I actually forgot to do my initial solution. Oh, let's try it again. But at least I know from the first titration, we're roughly needing about 30 milliliters, which is nice because it's going to have actually 1 more sig fig. So let's see if I have any leftover NaOH here. I have 9.62 left. Let's see if I can dilute this final sample, make use of everything. Let me just redo that dilution. So let's pull out a volumetric here. You see a lot of this lab work here is just trial and error here. So what I'm going to do is I have what looks like 9.62. I'm going to see sort of what's left over on my markings here. I have it at least 8 mils because I know I have at least down to the 50 mil mark. I don't want to go beyond that 50 mil mark because I don't have markings at this bottom part. So you might actually have some extra volume there, but I wouldn't actually be able to calculate for how much volume there actually is. So let's just transfer in 8 mils because that's safe. So for my calculations, I'm actually going to do my new dilution. Let's do 8 mils, right? So you notice I'm still not at the 50 ml mark. I can still read that well. So I have 8 mils, and again, I'm going to be ready to do my dilution here. Water over the volumetric flask. So this is another dilution. This time I've only used 8 mils. 8 mils. I'm going to toss in, let's say, 88 milliliters safely, right? That's going to pretty much fill up my my volumetric flask, right? 88 plus 8 is 96. And then again, just demonstrating that proper dilution technique here, I'm going to slowly drop it in sort of 1 mil at a time. As I get really, really close up to the top, maybe drop it in at 0.5 mils at a time, 0.5 mils, 0.5 mils. I'm getting really close, maybe 0.05. Just do this with a dropper. I want to be really, really precise here so that this is exactly going to be 100. Actually, with the magic of a virtual lab, I can even just copy and paste this. I can make as much of the solution as I want. I'll probably need to use that in a second here. But let's just try it out again. So I've now made my new dilution. I'm going to get rid of my old dilution. I forgot to take down my reading. Oh, out of luck. Let's try it again. Let's pull out a fresh burette or just a previously washed burette here. Fill it in with something more than half. So let's fill it in, let's say with 40 again. Again, this is in a virtual environment. It pretty much is going to be similar for multiple trials, but I'm just trying to mimic if this were in real life, this is what you would have to do. This time I'll make sure to take down my starting reading. My starting reading here was 11.22, right? Plus or minus 0.05. That's my initial starting reading. I'm going to have my HCl solution. Fortunately, I have enough of that there. That's why pipetting only fractions at a time, aliquots of it, is actually a little bit helpful. I'm going to demonstrate one with 25 ml pipette, and I'm going to do the others with 10 mils, just to show you can make a comparison between the two. So let's pull out a Erlenmeyer flask again. Let's actually pull out a couple, so we're ready. Oh, I actually have the other two left over. So I'm going to pipette. Here's my sort of more accurate trial. What I'm going to do here, I'm going to pipette withdrawal 25 mils, just like I did before. This, they tell me, is roughly 0.1 molar HCl. I'm going to dispense it into the Erlenmeyer flask here, dispense in the 25 mils. Don't forget to add the phenolphthalein. So add the phenolphthalein inside. Phenolphthalein and acid is still colorless, no problem. And now we're ready for titration. I double checked, make sure I've actually recorded down the initial volume. Yep, 11.22. And then now I'm going to toss it in. Again, just like we just did this, right? It's just good practice for you to do more titrations. I know I have about 25 mils in there. This time I'm going to safely toss in, let's say, 20 mils. So pour in 20 mils. That shouldn't be any problem. So it doesn't stay pink color. That means I still have leftover acid. I know it's going to be somewhere between maybe 21, 25 or so. So maybe I'll drop it in. Again, this is just trial and error here. Toss it in maybe 1 mil at a time as I get close to that 25 mil mark. Then drop it in a little bit smaller quantities, maybe 0.5 at a time. And then as I believe the pink color is staying for longer, maybe drop it in 0.05. I want to be as precise as I can. Let's see if I don't overshoot it this time. You want to be really meticulous as that color change appears within a matter of a drop. So the other one was 40.02, so it should be getting really close here. The total volume is actually increasing there. Kind of sitting at the edge of our seats here. I want to actually make sure I've added in my phenolphthalein. I can even add in a few other drops. I'm really hoping I did add in that phenolphthalein. So phenolphthalein. Right. Oh, so it's guaranteed. Yeah, it should be turning pink if it turned to base. So that's just confirming that. I can wash down. I should be really, really close now. I haven't even been counting how much 0.05. That's okay because I'm going to totally add a reading later on. So I'm just going to pour. We're waiting for this to turn pink. So we had NaOH here in the burette. Keep pouring it in. Oh, there we go. So again, I overshot by 1 drop. But again, the first trial is usually a waste anyways. In this case here, I'm going to take down the reading. I'm looking at about 43.65 plus or minus 0.05. So the total volume that I needed, let's see, 43.65 minus off 11.22. I actually needed 32.43, and that's actually the number I'm going to use for my titration. I think I do have enough solution for one more trial, so I'm also going to do that with the 25 ml pipette. You can just toss the solution out, take a new Erlenmeyer flask. I'm going to pipette 25 mils. Sometimes you totally run out of solution, so so be it, right? This started off with 100. I already wasted 125. There's 25 there, 25. So I probably don't have enough for the next trial. We can actually take a look here. If I pour in 25 here, so that one was fine. Let me see if there's actually 25 left. So I still about 30. Let's see if I can withdraw 25 here. This would totally just be for practice sake here, because what you realize is, oh, I actually used up all the HCl. You might be able to calculate, oh, what was the concentration? But now I have no more solution left over to actually utilize for your actual experiment. So always it's good to make up a big vat of unknown base, unknown acid. You might waste a little bit during the titration just to find the actual concentration. Concentration is intensive. It can actually figure out what the molarity of that stock container, stock bottle is. So it looks like I do have enough. Hopefully I have enough of my diluted NaOH here. I'll show this all on the OneNote and how we did the calculations. Maybe I'll top it up some more because now we're doing 25 mils at a time. So toss in, I have about 6 mils, so toss in 30. Maybe I'll toss in another 10, right? So now, again, I'm not confident if I will have enough for both trials, but let's just try it out. Make sure you drop in your phenolphthalein. Phenolphthalein into both of those there. We're deciding to test 25 of our unknown acid. And now I'm going to be ready to drop in my base because I know roughly it's going to be 32.43. I should be safe here dropping in about 30 mils. I'm going to make sure that I've tabulated down my starting number. I don't want to have to redo that part. So this one here, my burette looks like it's 3.67 plus or minus 0.05. I'm going to toss in 30. That should be safe. So you just unload 30 right away. That's what your first trial said, approximately what it was going to be. And then now what we're going to do is we're going to toss in maybe 0.5 at a time. So then this would be 30.5. So this would be 31, right? Now we're getting pretty close to the 32.43. So maybe I'm going to drop it in at 0.05. Right? And I'm getting really close here. So keep dropping it in. I'm looking for that instant when it first changes color. Right? So the first one gave me a nice ballpark here. Let's see how long this is going to take. Oh, there you go. Again, whoops, I overshot by 1. But again, that's another reading. Let's just take down that reading there. This gives me here 36.0, maybe 0.02, plus or minus 0.05. Let's find that difference in volume. Let's see if it was close or not. Even this is a virtual environment. It does simulate some random error. So 32.35. It's a little bit less than we had earlier. If I have enough solution, I'm going to definitely test this last one anyways while I have it. I do need to unload my burette. Remember, it's okay to refill your burette, no problem. Sort of not in a titration. You just can't do it while you're doing the titration. That's why you say you want to make sure you have somewhat more than half. I have about 14 mils in here because the 15 mils is marked down there. So let me just toss in here another maybe 40 mils if I have it. Oh, I don't even have 40 mils. I might totally run out in this case here. We're totally playing a gamble here. 16 into my Erlenmeyer flask here. I'm going to drag that in. Make sure you tabulate that first number. So this was 16 point, bottom of the meniscus here, maybe 22 or so, plus minus 0.05. I should have enough for about 30 or so, so let's just toss that in. So I'm going to toss in 30 safely, right? So I have my phenolphthalein in there. I'm going to pour in 30, right? Totally safe. I'm getting pretty close to running out of solution here, but I should be okay because I should have about 4 mils in there. The other one was only 32.35, so I should be able to add another 2.35 or so, give or take. So maybe I'm going to add 0.5. I'm going to add in 0.5, 0.5, 0.5, 0.5. So now I'm added in 32, and now I'm at the sort of probably the part when it should be changing color. Maybe I want to add in only 0.1 at a time. So I add in 0.1, I add in maybe once, twice, 3 times. Now I'm really, really close. Maybe I want to add in 0.05, right? This should change the color. Oh, there we go. And there we go. That's our perfect endpoint. When the first color change happens, we're going to take our reading here. And this one here says 48. We're going really close to the end of the burette here. 48.55 plus minus 0.05. We're going to switch over one last time to the OneNote. I'm going to show you some of these calculations here. Again, it was a little bit of work to actually do these titrations here. I demonstrated for you some errors that sort of came into play and how you would sort of address some of these issues. So with that, let's switch over to the OneNote. Okay, so this is the slide that we left off with yesterday. This was sort of the first part of the titration. This one we used the KHP standard solution, and we actually were able to find the concentration unknown NaOH really, really well. The only number I want to take from this slide here that we need to borrow from here is we had standardized the NaOH to actually be this 0.92 molar. So if you're wondering where I got the number, you can look back at the previous day. I'm just going to switch over to just a fresh slide here. Let's pretend that that 0.92 molar is an exact one. I'm going to show you with the last titration techniques that we just did there, how the rest of the titrations, how the calculations look like, and as well, hopefully try to show you how the error propagates as well. So let's just finish off what we just demonstrated for you. At first, I realized I didn't have enough NaOH. My NaOH here, so NaOH, the concentration, this one here would have actually had an error. I didn't do it for yesterday, so let's just assume it's exact for now. So that was 0.92 molar. This one here was the one that they said is give or take 1 molar, which it was. And what we're doing here in part 2 of our titration is we're going to titrate NaOH against HCl. The HCl, what they told me so far, HCl is going to be roughly 0.1 molar. Again, if you just took the NaOH solution straight and actually reacted to HCl, because the NaOH is almost 9 times, 10 times stronger than HCl, it's not going to take much and the pink color will slowly appear. So what you saw is we actually did a dilution calculation. The appropriate way to do dilution here is I started off with a solution. You notice I took a burette. The first time I did a dilution, remember I did that mix up and like, oops, I forgot the starting initial volume or whatnot. I'm just going to do it with the second time because that's where we got the rest of the numbers from. I used a burette, and basically what I did is I used sort of that last little bit of solution that I had, and I transferred in 8 milliliters into a volumetric flask. So I know the volumetric flask here doesn't actually give me lines graduating and actually marking the size. I know 8 milliliters from the burette. As long as I have one tool that can read the volume, we're still fine. 8 milliliters, we were really, really close. I know this was a 100 mil volumetric flask. So by the time I hit that mark there, I'm exactly 100. So what happens here is we had NaOH swimmers. They used to all be in 8 milliliters, and now I've purposely diluted down 8 into 100. If you remember from our dilution lesson, the moles themselves actually stay constant. The number of particles are actually still there. Dilution just ends up as our formula here, C1V1 equals C2V2. So the concentration is expected to drop. Our starting concentration, again, this is the number that I borrowed from yesterday, 0.92 molar was what we had. I used 8 milliliters of our volume. I want to know what my new concentration is now that I've been diluted down to 100 milliliters. So it's just this ratio 8 into 100. It's roughly 1 in 10. So 0.92 times 8 divided by 100. For this one here, remember we said we just wanted consistent units. It would be nice if I actually had the error for this, but I'll just demonstrate the error for the next part of the calculation here. Let's just say this is a true 0.0. It's a 736, so I'm just going to round it to 0.074 molar. So upon diluting it, you notice I've knocked the concentration. I had standardized this. I knew this concentration here really, really well, but because of the dilution, I now know this number also really well, and it's also much closer to the 0.1. This way my titration here will be a little bit more fine-tuned, a little bit more precise. Alright, so I'm going to just draw you a picture of that latter part here. What I did is I took the diluted NaOH, I filled in a fresh burette. So this burette here was just diluted NaOH with a concentration 0.074 like we just calculated. We had made a few, here's the starting reading, V initial, here's the ending reading, V final. Again, ultimately what we want is we want the difference in volume because that's actually how much solution you tossed in. And what I did is I tested it against my HCl started off with about 100 milliliters. I only tested off a 25 milliliter alicot. So 25 milliliters, that was from a pipette. This is unknown concentration HCl. I know it's roughly 0.1, but the whole point of doing this titration is to try to figure out what this number should actually be. Let me just copy down the numbers I had to the side. I also did 3 trials of this. Of course, I would have wasted more solution because the pipettes are actually 25 milliliters. But again, the advantage of doing 25 mils is actually it guarantees that the titrant, the amount of difference, you can actually do this name here. This is called the titrant volume. The amount that you're actually tossing in is actually something bigger than 10 milliliters. That's going to have one more sig fig than what we saw yesterday. So let's see how that looks like here. Just going to tally the numbers. The V initial for the first one was 11.22 plus or minus 0.05. The V final, when I overshot a little bit, 43.65 plus or minus 0.05. I can do the difference there. I'm just going to remind you here the titrant this time was NaOH again. You could have totally done acid in the burette and the base in the bottom. Just make sure you know which chemical is which, and the end just ends up as a stoichiometry problem. So that was the first one here. I had to reload my burette because now it's taking some 30 or so mils. So I reload it in between, that's fine. 3.67 plus or minus 0.05. This one ended up as 36.02. These are the numbers that I jotted down from our experiment from earlier. And the last one we tried here, I had to reload again. So this one here was 16.22 plus minus 0.05, and the total volume. Remember, I'm just taking the reading of what the burette says at that moment. I'm going to do the subtraction to actually figure out how much I actually dispensed in. So let's go through here, 43.65 minus 11.22. Although my sig fig rules here would let me keep 2 sig figs, unfortunately because the errors end up as 0.1, this one ends up as 32.4 plus or minus 0.1. That one was slightly overshot. I'm going to see if the other ones are a little bit better. 36.02 minus 3.67, 32.35. So that's sort of consistent. Well, if the first one was overdone it by a little bit here, I can still write 32. Still 4. Right, I'm sort of losing that precision. Let's do the last one here. I tried to be really precise towards the end here. This was 32.33 plus or minus 0.1. And again, this would be 32.3 plus or minus 0.1. Right, so I sort of had an indication maybe the first one would have been overshot, but even between the other two here, either they too were also overshot, but we're roughly the same. Earlier, we had one that was totally off as outlier. I totally just forgot about that one or dropped that one. In this case here, because these three are so similar to each other, when I take the average, this is usually the first part of the problem, what's the average NaOH that I actually use? I'm just going to do a very simple average. I'll show it to you with the error propagation. So basically, it's averaging these numbers. If I believe none of these are overshot, divided by 3. The errors end up averaging as well because I have errors on all of them. So that's also divided by 3, so that's also 0.1. Let's see what we get here. 32.4 plus 32.4. I know pretty much we're going to get something similar to this anyways, but let's calculate through. This first gives me 32.37 plus or minus 0.1, and again I'm back to 32.4. Usually in a word question, they'll probably set the number so it comes out a little bit differently. But this is experimental. This is what we get, so that's what we're going for. At the end of the day here, this is going to end up as a stoichiometry problem. We are titrating HCl against NaOH. This one here also is in a 1-to-1 ratio, NaCl and water. Let's just tabulate down the numbers that I have. This time I know the NaOH here is the base, so 32.4. One thing that isn't immediately clear here is you will notice because I did the dilution a little bit on the low side for the NaOH, my titrant volume is actually bigger than 10. Yesterday's lesson, my overall average volume dispense was only 9 point something. That only gave me 2 sig figs. Because our titrant volume is actually bigger than 10, we actually have 1 more sig fig here. So that's actually a good feature. We do want to have the base and the acid to be roughly the same concentrations, but we want to increase the precision if we can. One way why that happened was because I used a 25 mil pipette anyways, and that way I'm getting a little bit more detail. But nonetheless here, let's just carry through. My diluted NaOH I wrote down earlier was 0.074 molar. The HCl, I knew it was going to be about, 0.1 molar. But the whole point of doing this titration is to figure that out exactly. What I decided to test, this was called an alicot. We started off with a sort of a sample on the side. This was our unknown HCl. I didn't test the entire thing. I just pulled a 25 ml portion. I actually did that 2 or 3 times, so I actually got multiple trials. Each of the trials themselves is called an alicot. It's a small sample that I'm testing. Hopefully, sure, I end up wasting the solution. Here's another hint here. Especially when you're dropping in base, the total volume actually does change, but you notice that in none of these experiments did I actually care the final volume. It was just sort of unfortunate when I drop in base particles to kill off the acid, it just added up the total volume. It would look like it dilutes, but ultimately, when you have a good count of how many moles of acid particles there are present, eventually that acid was just in 25. I'm going to always be divided by the initial volume. So let's see how this works out. Let's find what is the unknown HCl. We're going to start off with the chemical that we know more. So I'm going to convert that to 0.0324. That's going to be plus minus 0.0001. Just going to show it to you with error. So this is going to be liters. This one here is NaOH. I'm going to use the concentration. Technically, I should have had an error on this one as well. When we do our titration lab, you definitely will. 0.074. In this case here, I'm just going to treat it as if it were exact. When you do the mole ratio, there's no error on that. This one here does say a 1-to-1 ratio. Be really careful. Sometimes it really is not 1-to-1, so make sure you have a balanced equation. You might be missing this step. So one more comment on that afterwards. This part here, so basically all your units cancel out. This, great, it's counted the number of moles of acid. Let me just actually write that down for you. This counted for you, moles of acid is counted in the Erlenmeyer. And then again, what we wanted is we wanted the starting concentration. I don't want the acid after you mixed in the base, after you've sort of destroyed the sample and diluted it. I don't need that concentration. I just have this many moles of acid, this many swimmers, used to just be in 25. So when I actually divide it by the volume, I'm actually just going to divide it by 0.02500 liters. That was the initial volume of the acid. And therefore, I would get the initial concentration. You're totally right, initial volume of acid. You're totally right, I have completely destroyed the sample, but if you remember, this sample came from an aliquot, it came from a stock bottle, it came from a big vat of more acid. If I know the concentration from this calculation, the concentration that I destroyed is actually going to be the same concentration as my whole bottle, and now I'm ready to use this bottle for other experiments. So let's just type our way through here. Basically, it's going to be 0.0324 times 0.074, that was the concentration, divided by 0.025, and that gives me the concentration. We can still do a sort of mental check here, 0.0959. If we had the dilution, so from previous, I only had it to 2 sig figs. Unfortunately, this was only 2 sig figs. Unfortunately, I'm still limited to just say 0.096. But if I had, for example, the titrant volume for NaOH was bigger than 10, I would have this to 3 sig figs. With 3 sig figs, I can actually keep that 959 in that case. The whole point of a titration is to be really, really precise. They already told me, yeah, it's about 0.1, but now I actually know a little bit more precision. It's actually 0.096. What about the error in this case here? In a typical experiment, I've showed you you have an error in the volume. You would normally have an error in the concentration, so you need to prop that as well. You'll have an error in the pipette reading as well. You'll need to sum up all those errors there. Remember, errors, you have to add up the relative errors. So what we're going to do is we're going to do something like do a plus minus. We have the error in the volume, so how bad is 0.0001 out of 0.0324? We would have had an error on the concentration. Again, I'm just going to totally make up something right now. 0.001 divided by 0.074. Let me just write these down here. This is the error in average NaOH used, so the average in titrant volume. This one here would be the error in the concentration, if I had that from yesterday. And then I would have the error on a pipette. This is usually typed for you on the actual pipette. You can actually, the manufacturer would actually tell you their given error. I know a pipette is really, really precise. It's 0.02500. I think our pipettes here is 0.00. Usually it's like 2 or something like that. Those ones that are adding the relative errors there, that would give you the overall percentage. And ultimately you want to convert it back to absolute. So I then multiply the 0.0959 again. So let's see what we get here. 0.0001 divided by 0.0324. This gives me here, this is about a 0.3 fractional error. 0.001 divided by 0.074. This one is a 1.4 relative error. 0.00002 divided by 0.025. That one gives me a 0.08% or relative error there. So in total, I'm looking at 1.7, 1.8 or so error, but I need to multiply it again to actually get it back to an absolute. So when I report my final answer, let's see how bad this is. I would type in the numbers completely so that way I don't accumulate any rounding errors. Remember, when you're doing math with this one here, you don't actually need to type in the times 100. That was just for a nice reference for you here. I'm going to take all those errors added up, so it's relative error 1.7% or so, times it by 0.0959. It's giving me plus minus, based on the errors that I had listed, this one, it gives me 0.00167. We're going to do a mental check here. We're going to round our error to 1 sig fig, so 0.002. Can I leave my final answer like this? Does it line up? In this case here, phew. When the error is 1 sig fig, it actually matches up here, and I actually do know now the concentration of HCl. is very well precise to 0.096, 0.002. Again, it would be assumed you actually had a huge stock bottle of this one here. Now that you know the concentration, you just pour a fresh sample and you'd use that for your future experiments. But there we go. Over the last two classes, we've just been looking at how do we actually conduct a titration. As you consider doing like your IAs and other experiments in class, titration is a very common technique in order to find an unknown concentration. Thanks, guys. Take care.